Okay, so now let's talk about L'Hopital's rule. Although this title makes it sound as if it's Hospital rule, it's actually pronounced L'Hopital. You can impress your teacher if you watch this before they teach you. L'Hopitals. Alright. Now that we figured out how to pronounce it, that's always the first step of any math tutorial. Let's go over what it is. If f and g are functions that are differentiable on the open interval ab, and if the limit of f of x divided by g of x as x approaches some number c produces an indeterminate form, such as 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, and other forms like that, then the limit as x approaches c of f of x over g of x equals the limit as x approaches c of the derivative of f of x over the derivative of g of x. So now you have this definition. Let me show you one way that you could find it useful. So let's assume you have something that says limit as x approaches, how about 0, of sine of x over x. Now, if you were to directly plug it in, you would end up getting limit as x approaches 0, 0 over 0. Now, like I said before, that's an indeterminate form. That means you can't have this form. If you were to divide 0 by 0, that just doesn't happen. If you attempt to do it ever in your life, the universe explodes. It just combusts. It explodes. So don't ever try to divide 0 by 0. It just won't work. Indeterminate. The same thing goes for infinity over infinity. If you try to divide infinity over infinity, kablam! Another explosion. Don't do it. No. Bad. Indeterminate forms are forms that cannot be simplified. Alright, so now if we were to use our rule, our L'Hopital's rule, we're going to take the derivative of sine of x. Sine of x is cosine of x. I found my limit. And then our derivative of x is 1. So then you can just plug in here now. So cosine of 0 is 1. 1 over 1 is 1. Alright, so that's when it can be useful. So L'Hopital's can be really helpful sometimes, like in this case, but in other times you can like factor out stuff, you can do other things. So let me erase this, I don't want to run out of space on the bottom. So assume you had something like limit as x approaches 4, you had x squared minus 16 over, I think it's x minus 4, right, something like this. You could use L'Hopital's rule, because if you were to plug in, you get 0 over 0. But really, in this case, what you should do is you should factor out stuff. So this would end up being x minus 4, x plus 4, and then x minus 4. Keep forgetting my limit. Alright, and then this stuff would cancel out, and you plug in 0, you get 4. You could always do that, right? Or you could do L'Hopital's rule, so you end up getting limit as x approaches. My goodness. I just realized I did the last one wrong. I was plugging in 0 instead of 4. The answer would have been 8. So, and then derivative of 2x would be, or of x squared minus 16, 2x, and then 1, so you'd still end up getting 8. So either way works. You could use L'Hopital's rule as kind of like a backup, a check, because most of the time you only want to use it when you can't factor it, rationalize something, cancel stuff out, you know. Okay, so now let's do an example problem where you might have to take the derivative of the denominator and the numerator more than once. So here we have the limit as x approaches infinity of x cubed divided by e to the x divided by 2. So right off the bat, I'm noticing that if I were to plug in infinity, I'd get infinity cubed over e to the infinity divided by 2. So that just ends up being infinity over infinity, right? E to the infinity can't really divide infinity by 2 because you just can't. So e to the infinity is just infinity. Infinity cubed is just infinity, right? Infinity over infinity is an indeterminate form. So what we have to do is we have to take the derivative. So limit as x approaches infinity of 3x squared divided by 1/2 e to the x divided by 2. But notice here that if you were to plug in infinity into the numerator and the denominator, you would still get the indeterminate form of infinity over infinity. So what we're going to have to do is we're going to have to take the derivative of the numerator and the denominator again. Limit as x approaches infinity, 6x divided by 1/4 e to the x squared. Alright, we're getting a little bit closer, but you notice here it's still infinity over infinity. Let's keep deriving. Limit as x approaches infinity. You know that one song in Nemo, just keep serving, just keep serving? I'd like to think that my motto here is just keep deriving, just keep deriving. Doesn't quite have the same catchy tune. Alright, 6 over 1/8 e to the x divided by 2. Okay, so now we've finally gotten somewhere that we can handle this infinity. So, like I said before, if you were to plug in infinity here, this entire denominator would just be infinity. It just works that way. Limit as x approaches infinity of 6 over infinity. Alright? So now you're probably thinking, wow, we're done with the problem. But there is a way to simplify this more. Alright, so I notice that this denominator is extremely large, right? So let me show you something. If we were to have 1 over 5, 1 over 50, and 1 over 500, let's compare how their actual numbers, their decimal numbers work. 1 over 5 is the equivalent of 0.2. Okay? 1 over 50 is the equivalent of 0.02. 1 over 500 is the equivalent of 0.002. Right? Ooh, excuse me. Just got a huge whiff of expo marker. Okay. So you're noticing as the denominator gets bigger and bigger, you'll notice that this number actually gets smaller and smaller. It gets closer and closer to 0. So, if our denominator is extremely large, we can say that our limit is going to 0, right? Oh, that expo marker got me really... Ugh. So this is a rule that you can apply to a lot of L'Hopital rule problems, and it's very useful to know, because most of the time teachers don't like it when you leave it as 6 over infinity. Always know that if infinity is in the bottom, if infinity is in the bottom and a constant is at the top, you can simplify it to be 0. And that's how you use L'Hopital's rule to simplify a limit when you can't rationalize, factor, cancel stuff out, or just do anything you would normally do in a limit problem.